It's 5 to 7.
I would shoot for an 8 o'clock.
8 o'clock?
8:15.
Yeah. Okay.
That's cool. Okay. You're good.
Yeah, we will be recording. Make sure he repeats the question. If he doesn't, I'm gonna yell at him. You guys can yell at him too.
Hi, I'm Bart Paulson, and I get to come here and talk about things that you guys already know. So you get to give me lots of feedback. I teach people the rudiments of working with data. So most of my stuff is very, very elementary in terms of trying to get things so people can understand it. Actually, it's kind of nice because it turns out that most of the people who are going to be using the stuff that you do in data science are going to be dealing with it at a pretty basic level. And so it's a big advantage to be able to, for you also to be able to present to people who are not experts in their own field. My day job is I'm a psychology professor at Utah Valley University, but I teach statistics exclusively. And I am also an author for lynda.com, who does online training, and I have my own business, datalab.cc. There's a little thing down there. And I actually have already recorded and edited this entire presentation for Data Lab, and it's halfway posted already. By midnight, it'll all be up on the website, and you'll be able to get high definition and professional versions of this stuff. But it won't have your questions. It'll have just the stuff that's there already. Now, last time I got to talk about something that was fun. It was an intro to data science. I got to show a picture of Ada, Countess of Lovelace. This time we decided, how about we talk about something boring as hell? And we go planning data science projects. Well, I'll tell you why. Ready? Let's take a quick look here, because we all know data science is sexy. The Harvard Business Review told us so. That's why we're here. On the other hand, planning, not so much. Then again, you know what else isn't sexy? Losing the project or funding because you don't know what you're doing. Wasting your time because you constantly have to backtrack or you're making things up as you go. Forgetting to do things. Like getting variables coded in the right direction or knowing what the data set's called. Train wreck teamwork. I've observed this personally many times where nobody has any idea what anybody else is doing. And you have 4 people doing the same thing all at once in different ways and nobody's doing the second step. Not being honest, for instance, not leaving time for ethical requirements. I don't know how many of you guys have actually had to deal with. Have any of you actually had to deal with federal ethical requirements in working with data? It's an extraordinary pain. And if you sit around and say, okay, now I'll get ready, you say, oh wait, I have to go through a 6-week-long IRB training and then get certified and wait to hear back. Then I have to send my stuff off to the Institutional Review Board. If you don't get this stuff started, 6 months ahead, you're dead in the water. So, and also, things like hypothesis switching and fudging reports because you can't even remember what you did, and also getting in trouble. In my field, social psychology, this has come up to the forefront because it turns out that there's a lot of researchers. Now, there have been some who've been engaged in outright fraud. They've been totally making stuff up. They're not employed anymore. But there's been a whole lot of them who apparently there's like 50 years of cherry picking. Conduct like 12 versions of the study, 2 of them work, publish those. Technically not illegal, but it means that people can't replicate your research and it looks really bad. Anyhow, so none of these things are good. You don't want those. So instead, you want to learn how to plan and then be sexy. So you can keep that going. So what we're going to talk about tonight, I'm going to give an extraordinarily quick overview of a few common planning models. And then I'm not going to talk about any of them in detail because I have a sort of an amalgamation I'm going to put together. Now, some of you may be familiar with some of these acronyms and initialisms. There's CRISP-DM. I'll explain these in a little more detail in a second. There's SEMA and KDD. In a different field, but one I talked about in my last talk is my favorite is AWESOME. And then there's what I call the Data 12 step that I made up yesterday. And now there's some data about how common each of these are. KD Nuggets, you guys familiar with that site? It's a fabulous place. Did a poll back in fall of 2014 about how common methodologies were for analytics, data mining, and data science projects. And CRISP, despite being sort of kind of maybe not alive, a zombie methodology or something like that, almost 50% of the people reported using some version of CRISP. Much smaller percentage used SEMA, slightly smaller KDD, and now AWESOME wasn't included in that. It's not an official methodology, and Data 12-step, I just made it up, so nobody uses it. I'm going to give you a little more information about each of these because they may have come up in your situations. You may have heard the terms. I've heard CRISP come up in these talks here once, and I had no idea what they were talking about. So here's what it is. CRISP stands for Cross-Industry Standard Processing for Data Mining. Actually, are any of you familiar with CRISP? Okay, it's just Ben. I think Ben Taylor mentioned it. Yeah. Cross-Industry Standard Process for Data Mining is developed back in 1996 by SPSS Teradata. We have a Teradata person here? Okay. You guys use it all the time, right? That's okay. I don't think Teradata uses it. Daimler, NCR, and OHRA, which is an insurance company. And so that was back in 96. Unfortunately, the web page is dead. And the only people who make any reference to this at all is SPSS. So it's sort of their baby now, and nobody else touches it. But it's there. It exists as a methodology. I'll say more about it momentarily. Well, right here. CRISP consists of a few steps in planning a data mining project. The first one they call is business understanding. That really is, what is your goal? But the important thing is it's a goal in terms of a business goal. The idea is that you're working in a professional setting. Now, I work in academic research, so we got a different set of stuff going on. But you guys are going to be working in the professional world. You're going to have clients, and they don't just want to know that this is an interesting subgroup that shares things with this. They want to know, what am I going to do next to make more money? And so that's the business understanding. What is the goal from an actionable, concrete way of reaching the business's goals? Second one's called a data understanding. Again, it's kind of a weird term, but this means what data is available to you and how can you apply it to reach your business goals. The other ones are a little easier to deal with. Data preparation, knocking it into shape, and modeling of one kind or another, and then the evaluation of how well did it all work. So that's pretty, makes sense. CRISP, you'll see the other ones have a lot in common with this. The next one, oops, excuse me, there's deployment also. Put it into action. And that makes sense if you're developing a data product, like a recommendation engine or a friend finder on a social network or something like that. So you develop it with a small subset of data, and then there really is a launch where it goes out and starts working. In my field, this would simply mean that you're now going to publish the paper that has your model in it. Next one is SEMA. If SEMA was developed by SAS, and so, CRISP is SPSS's, and SAS and SPSS, they got their thing going on. So SAS has their own thing. It's SEMA, and also specifically for data mining, but according to the KD Nuggets poll, less than 9% of people are using it. But it's got steps, and it's an acronym, so it's pretty easy. The first one is sample. Get your data, where you're going to pull it from, then explore the data, which we all know you should do. Modify it as necessary, model it, and assess. That's it, right? Now, of course, each of these organizations has documents that goes into excruciating detail about each one of these. I find that stuff to be a brain cramp to read. I've got the documents. I don't want to read them. Next one, KDD. Any of you familiar with, well, anyhow, knowledge discovery and databases. You should know that term. It's back from 96, paper by Fayed et al. Again, it's something I'm a little bit, know that it exists, but it's low usage. But here's the idea with KDD. First, selection. Again, find your data, pull on your data, do a little bit of pre-processing, because we're specifically talking about data mining in this context. the transformation to get it into whatever you need, the data mining or modeling, and then the interpretation or evaluation. Fine. You guys see that there's some really strong consistencies across all of these, but you have to change it a little bit to be able to put your registered trademark thingy on it. There's a few others. Interestingly, I kind of like this one because if you go to the Wikipedia entry for CRISP DM, in the first paragraph, it talks about how it's being replaced by this updated model called the Standard Method for Analogical Models. Some dude just made this up, wrote a Wikipedia page himself and says this is the successor. And it's got a big thing on that page that says this page is marked for deletion, so I had to take a screenshot to make sure it was still good. And his page mostly consists about bitching about CRISP. And it says, when you do methodology badly, then there's problems, but we knew that. There's also a decision model and notation. You guys familiar with, does anybody know this stuff exists? Decision model and notation is like this extraordinarily huge involved framework for developing these kinds of things. It's like the tax code. It's enormous, it's huge, and I can't possibly imagine how knowing anything about decision modeling and notation will help you get your work done. Mostly seems like a way to lose a few days. Anyhow, many others, and I don't worry about them. Some of my colleagues refer to this sort of stuff as methodolatry. You've gotten lost and off track. You can also call it planning porn if you want. Not very useful. Awesome, a different thing. I talked about this in my last talk here a month or so ago. Hillary Mason, everybody's favorite data scientist, and Chris Wiggins in a blog post in 2010. What means that's really nice about that is A, it's free, B, it's really short. It's called the Taxonomy of Data Science. So look it up. It's on Dataist, and that's not an active blog. This last entry was 4 years ago. But the post is still there because for me, this is a functioning Bible of data science. This is the one I use all the time. Awesome stands for obtain your data, scrub your data, clean it up, get it ready, explore the data, model, and interpret, where they use the N for interpret. It's the easiest one for me I can remember this one. I actually know what everything stands for, and they give some great examples of technologies you can use for each one. I mentioned this in my last talk, so I'm not going to talk about it much again today, except to say I now decided to create something called a data 12-step, because those of you who work with SAS, you know about the data step, and I'm a psychologist, so we can talk about 12-step, but anyhow, just my own creation, kind of putting together all the other things and try to fill in a few gaps. I think social logistics was a big one that was not in any of them. And sometimes state the obvious because sometimes people forget the obvious, like labeling the axes on your charts. Anyhow, I'm going to run through these very quickly because then I'm going to go over them in more detail. Define your goal, organize your resources, coordinate the people, get data, clean the data, explore the data, refine it, model it, interpret the model, present the model, show it to the people who are paying you for it, deploy the model, and then revisit the model. Okay, so that's the idea. And it's not intended as a replacement for any of the other ones, but just sort of breaking it down a little more detail. So let's talk about these one at a time. Define your goal, okay? Something I used to teach research methodology, and one of the things I would tell my students when they were writing their research papers is get a tiny little sticky note. You know, the ones that are this big? Write down the point of your project on that, and you can only put like 6 words on there. And stick that on your computer screen, and then everything you do from that point on has to relate to what's on that sticky note, or you're wasting time. So define your goal. Know what you're trying to accomplish, especially with your client, because we found out sometimes that what the client tells you and what they tell you that they want and what it is that they actually really do want are not identical. And sometimes it takes a while to figure out exactly what it is that the client wants, what will be most useful for them. Because they might come to you and say, we must do Hadoop cluster to launch our 4 Excel spreadsheets in. You know, that's not it. You got to get through it. And also make your goal, whatever it is, business relevant and actionable. Again, that's something foreign to me as an academic researcher, but I know in the real world, people are going to pay you if it improves their business. I got a huge business pitch from a guy the other day who wanted me to pay him, I'm a one-person business. He wanted me to pay him $500 a month to do I don't know what. And we talked for like 4 hours, and I still couldn't tell what he was going to do for me. Except he says, it'll make a big difference. I don't know what you're talking about, so it didn't work. Make it clear, make it actionable. Okay, organize your resources. So document your process. I'm going to assume all of you, if you've done more than one project, you have been burned by bad documentation at some point. And you go back and you have no idea what that stuff is because you were in the flow and you were creating variables and data sets and you were doing analyses and you didn't keep track and you don't know what it is. If you're like me, when I write code, I document obsessively. And I know it's not necessarily the best thing. I comment every single line, because I have to know what it means when I go back to it. Document your process. Who's accountable for things? If you're going to keeping billable hours, this is a good way. Also, the idea of reproducible research. I'll talk about that at some other point, not tonight. And version control. Just who's going to do it? Where are you going to store your files? Now, how many of you are actually collaborating right now in the global data competition? Anybody in here actually competing in the global data competition? Rock on, one person. The rest of you, get your acting gear. I'm exempting myself, I'm a teacher. Okay, here's what you need to know. You gotta have a way of collaborating. And stuff like Google Drive, Dropbox, Microsoft OneDrive, they all work great and they allow at least some version of simultaneous collaboration, which I find to be really important. Anybody here fluent with GitHub or SourceForge? Yeah, great way. Okay, if you can make it work, go for it. Anyhow, next is, what kind of hardware and software are you going to be using? Because not everybody's going to have a proprietary version of installation of SAS because it's really expensive. In fact, let me just ask, do any of you actually use SAS ever? One person in here. The last time I used SAS was 20 years ago. Can I assume you guys are primarily using, how many of you use R at some point? How many of you use Python for data? I know there's a big one. I'm not thinking clearly. What are the other options? MATLAB, right. Who uses MATLAB? Okay. Scala, Stata, Spark. Okay. You just write your own stuff in assembly code and you run it from there. Okay. Well, the point is you need to be able to share tools. If you're going to be collaborating, at the absolute very least, you have to be using a common data format that everybody's tool can open. And if you're writing code, you all need to have the same thing. So if you're writing in R, everybody needs to have R installed. Heaven forbid, strangely at my school, almost everybody uses SPSS. It's what I'm best with. It's what I grew up with. It's what's used in my field. But I keep telling people, you have to switch, you have to switch, you have to switch. It hasn't happened yet. Working on it. Standards and style guides. Anybody here familiar with Google's R style guide? Okay, this is a good thing. So if you actually want to know, how should you name your variables? Should you use bumpy caps? Should you use dots or underscores or what? Google has a style guide for R. It says, name them this way. And should you ever use equals as an assignment operator? The answer is no. And Google's got a ton of style guides, practically everything. And it's nice because it makes the code more readable and easier to share, which is really important. Also, really simple stuff. It's embarrassing, but ISO 8601, which is date formats, date and time formats in ISO. I don't know if you guys have had to deal with people coding dates in 17 different ways. If you go to ISO, there is one true way to code dates and time. Actually, it's a little bit of variation on that, but I strongly recommend if you're going to be working with anybody else, you settle on this, and I think the ISO guidelines work great. So it's year dash month dash day, right? Anyhow, there's those. Coordinating people. Data science is inherently a social project. Very few people can do every element of data science very well on their own. That's extraordinarily rare. You have to collaborate with other people. And part of that's because people have very different skill sets. A wonderful exercise you can do, I'm not going to do it, but you can build a little profile. I could give you all a little 3x5 card and say, okay, here's 5 different skills that go into data science. Make a little bar for how good you are at each one of these. You're going to have different profiles, I guarantee it. And what you do is you actually try to assemble a team by getting it so that the 5 bars are approximately the same height when you add them all together. So you don't have everybody who can code, but nobody who knows how to do budgeting. Anyhow, so you're looking for complementary skill sets. Now, again, you may just have to work with the people who you're with at work, but it is always good to reach out. And by the way, my best things as an academic researcher, my favorite work has been when I've been worked with people in very different domains than mine. My best publication, I'm a social psychologist, but my best publications are in law and dance. And it's great stuff. Contact info. I can't tell you how many times I have students sit around, there are like 7 of them, and they're all trying to write on little scraps of paper their phone numbers and their email. To make a Google Doc and share it immediately with the information, that's easy. Scheduling, you have to know when things have to happen. Do you guys use scheduling software? I mean, do you use something so everybody's on the same page, subscribe to a calendar? I know this is stupid stuff, but this kills projects. And then the handoff process. Who's going to get it next and when and in what format? Again, yeah, I get it's idiotic that I have to mention this stuff, but I've seen the projects go bad. Next one, get the data. Yay, real data science. What data exactly do you need? And the idea here is you could get some sort of existing data. Maybe you got proprietary data that you already have and is already in shape. Wouldn't that be wonderful? Open data is available if you can find it. Truthfully, I cannot navigate the open data system. I have yet to find a single data set that I was actually looking for that I could download and then open. I must be retarded. I can't make it work. Anything, anything. Even census, which is, this stuff is supposed to be easy. I can't make it work. Sorry. And external data sets. So data that's ready to go, but it's either belongs to somebody else, so you got to pay for it, or you got to ask for permission, but it's available. Again, between those things, you probably can get everything that you need most of the time. On the other hand, you also have the option of gathering data. So for instance, you can do APIs. So if you want to get like Twitter data or something from Google Trends, you just get the API. You can scrape data, get HTML tables off the web, and you can do that if you know how. You can do experiments. And so have any of you ever done A/B testing? So, you got a web page and you can put up a couple of different versions of it. You can do, there's very rudimentary simple A/B, and it can get incredibly complex. On the other hand, there's the totally non-digital kind of research, which is what I am trained in. I actually did everything with paper and pencil. I would hand it to people and they'd fill it out. We would do experiments where people actually showed up in different physical situations and we got responses from them. It's still very useful research. It's still very useful and you can do it. Okay, clean your data. In this case, I'm simply talking about it, making it so it will open up. So for instance, a few months ago, I organized an event down at Utah Valley University where I teach called the Utah Data Dive. And it was a wonderful event and where we had about 60 people show up to help 2 nonprofit organizations, the Springfield Museum of Art and the Utah County Crisis Line, take their data and do something useful with it. Both of them had their data in Excel spreadsheets. And one of them actually had a bunch of their data, literally paper and pencil. Here's the piece of paper with our month, our stuff on it. That stuff's not ready to go in R. And it actually took the 60 people a full day to get these spreadsheets into shape to then start modeling them the next day. You guys, you've heard the thing, it's 80% of it's cleaning up. That was true in our experience in this one. And it's because most people keep their data in Excel. And if you've worked with Excel, you know that you can put lots of tables and charts on a single spreadsheet, and you can put macros in, and none of that stuff goes in nicely into anything else. So you just have to find ways to deal with that. By the way, how many of you would say that you are very, very comfortable working with data in Excel? Okay. Interesting research came out not too many months ago, and it basically said that, guess what? Almost no matter what your job is, you have to be fluent in Microsoft Word and Microsoft Excel, just because that's the lingua franca of the organization. You have to know how to work with those. Excel's not hard. You can find 1,000 online tutorials for Excel. Just get a little bit. I mean, just knowing how to sort data without totally screwing up. If you've ever worked with Excel and accidentally sorted one row without sorting everything else and didn't catch it, and then transposing data, which is a good thing, and how to propagate patterns in the data. Guys, that'll take you half an hour to learn. And it's immensely useful. What's funny is the things that have impressed my students more than anything are not my deep theoretical skills on social psychology or my understanding of arcane statistical technologies. It's when I know how to search for hidden characters in Word. They go, ooh. And how to set up a spreadsheet. It gets you an enormous distance. And it reminds me, by the way, of the American Psychological Association talks about their methodological guidelines. And they say, use a minimally sufficient design. Use the simplest possible tool for the job. And frequently that's Excel. Anyhow, Hadley Wickham of R fame. Hadley Wickham, any of you, do you know the name? He's Mr. ggplot, and also now employed by RStudio. Hadley Wickham has a wonderful paper called Tidy Data. And he has an R package by the same name. And it talks about, make it so the data is usable, please. It's very obvious stuff, Data is a collection of values. Every value belongs to a variable. Every variable belongs to an observation. You should have one variable per column, one observation per row. And the reason he has to say this is because it doesn't always happen. He says, one of the worst things that can happen is when people code data with colors in Excel, because that does not transfer into a CSV file. And he says, so please, by the way, when I get home later tonight, aside from the fact that I will finish getting all of the edited videos up onto my webpage, I will also put the links for Wickham's Tidy Data and a few of the other things I'm going to mention on here because they're really, really nice to have. Jeff Leake has some information on sharing data. He's got a wonderful paper called How to Share Data with a Statistician. It's actually on GitHub. And everybody should read it. He also has a book, a short book called Elements of Data Analytics Style. Is anybody familiar with that one? It's a great book. You can read it in a day. Okay, he sells it on LeanPub and he also sells it on Amazon. Just very basic concepts, and it includes a very long data analysis checklist. It's about 3 pages. Just basic things. Did you do this? Did you do that? Did you do this? And it's wonderful stuff. Okay, we're back. We're still on cleaning the data. You can do it in Bash. If you're handy with the command line, that's actually a great way to clean data. Python and R, there are packages for each that make it very easy. And again, Excel, especially because most of the data will come to you in Excel. Nice to deal with it in its native environment. Okay, explore data. Get a feel for your distributions, check for shape, extreme values, gaps, linearity, check for the validity of your assumptions, make sure there's not something horribly wrong in there. I spent a time downloading a very, very large data set and then noticed that half of it was not a number. So we had to fix that. Mostly graphics. By the way, as far as I'm concerned, the single best tool for exploring data is Tableau. Anybody here use Tableau? Okay, Tableau and Tableau Public, it's a drag and drop interface, but it allows you to sort, do pivot tables, and to drill down in a graphical manner faster than anything else I know. Just boom, 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 boom. It's not good for doing a statistical analysis. There's a lot of things Tableau is not good for. It's not necessarily the most flexible program in the world, but I think in terms of data exploration, it's going to be fastest and easiest in Tableau. Even though I know you can do it in R, I know you can do it in Python, it's just faster in Tableau. By the way, I think I mentioned this in my last one about O'Reilly's data science salary survey. There's an average increase of $2,000 a year for each additional software tool you know how to use. So if you can throw Tableau on there, assume you'll get 2,000 bucks more a year, okay? Refine your data. So this is after it's been cleaned. And this mostly has to do with data reduction. So most of the time, a data set has more than you can reasonably use in it. And so you have to find ways of simplifying. Now you might do something like principal component analysis or cluster analysis or factor analysis or what have you. You might also just use subsamples of data of a very large data set. You can also do feature selection and creation. Again, ways of boiling it down because not everything in your data set's informative, and sometimes, I still love when we had the talk about the Taylor Swift competition. Were any of you here when Anthony Power was talking about that? It was because it's a large data set. How big was it? It was big. The Taylor Swift data set was big. But Anthony, he says, well, the only thing I have to work on is my 8 gigabyte MacBook Air. So anything I do has to fit onto there. No Hadoop clusters for him. It's going on his MacBook. It has to fit in 8 gig along with the. And so he basically said, I whittled it down to 7 variables and just ran from there. And he actually got to 100% accuracy when he figured out that there was an unintentional pattern in the data. But he got phenomenally accurate with a tiny, tiny subset of the variables and also by doing feature creation. Anyhow, modeling the data. So you might be doing linear logistic regression. Regression is always a great way to go. It's a great way to start. Maybe you don't want to finish there, but you guys know about ensemble models, right? Linear regression should be a component of your ensemble model. It goes in there. Logistic, of course, if you have a binary outcome. You can do decision trees or k-nearest neighbors or support vector machines or whatever fancy stuff you have. I'm not going to talk about these, except to say that these are one element in the entire data science pipeline. We like to focus on modeling. It's only one step. And in fact, at this point, I'm going to have a little brief interlude with our friend Moses. I came across a wonderful article called The 10 Commandments of Applied Econometrics. Recent article published in 2002 by Peter Kennedy, and I'll give you guys the link. But here's what he says. Thou shalt use common sense in economic theory. Meaning you don't have to do everything, you don't have to reinvent the wheel at every point. A lot of things are very obvious, and if you have a little bit of theory about the field that you're working in, obviously he's working with economics data, right? You guys probably aren't, I'm not, but if you know the field, then there's a lot of things that are simply impossible, and there's other things that are very likely. You can use those. Thou shalt ask the right questions. Part of that has to do with sometimes, if you think about it in terms of techniques, I was preparing a course for lynda.com on using R. And I thought it would be amusing to show how to make pie charts in R, because we all know pie charts are bad, right? I can make a pie chart in R. I tried to make a pie chart in ggplot2. Has anybody here ever done that? It's because it doesn't do them. You have to do it as polar bar charts. And I couldn't make it work. It was a nightmare. And so I spent like an hour trying to figure out how to do a stupid pie chart in ggplot2 and realizing, well, the reason it won't let me do that is because I'm not supposed to. That's it. That's not a bug, that's a feature. It's saying don't do it. And it's the same thing. When you struggle with trying to get the data to fit into a particular paradigm, when you struggle with a particular procedure, maybe it's because you shouldn't be doing it in the first place. Maybe the question wasn't right in the first place. Thou shalt know thy context. Kennedy says, know the phenomenon, its history, institutions, operating constraints, measurement peculiarities, cultural customs, and so on. Thou shalt inspect thy data. So that's he's calling here for exploratory data analysis. Thou shalt not worship complexity, which has a corollary. It's got two corollaries. I like these. He says, thou shalt not apply asymptotic approximations in vain. He says, use the fancy stuff if you need to, but chances are you don't. Chances are, most of the time, it will work just fine with an extremely simple model. In fact, talking with people who do actual sort of business consulting statistics, they say it's embarrassing how often really all they're doing is creating pie charts in an Excel spreadsheet, and they get paid $1,000 an hour. I said, it was really simple. And trying to tell people, I remember having a conversation with somebody, they're asking about a very sophisticated technique, and I said, why are you doing that? What you need is a t-test, which is the simplest possible inferential test there is. I said, that will answer your question. That one right there. You can do that one by hand. Also, Kennedy says, thou shalt not talk Greek without knowing the English translation. I had something I would tell my students when they were writing their research papers. Sometimes they'd give me these very long quotes in the method section of their paper. And I said, oh, that's because you copied it out of another paper. And they thought that by putting it in quotes and giving the reference, that meant it was okay. And I said, well, no, the reason you're quoting is because you have no idea what the hell it's saying. And it says, you have to paraphrase. You have to show me you know what it means. And the same thing's true for you guys. You have to be able to explain. And sometimes the problem is you can use procedures that you actually know how to make them work, but it's really difficult to explain. It's hard to explain path analysis. You guys familiar with path analysis? It's for correlations between variables. It's a pain. And it's very hard to explain it in a meaningful way. I can do it approximately, but not meaningfully. Thou shalt look long and hard at thy results. He says, thou shalt apply the laugh test. That is, ask oneself whether, if the findings were carefully explained to a thoughtful layperson, that listener could avoid laughing at you. And that's important. Thou shalt beware the costs of data mining. Now, this is important because they're not talking about the data mining that you guys do. What they're talking about here is wild, undisciplined fishing around for the first statistically significant finding that you can get. Woohoo! That's irresponsible. That's bad. Again, that's cherry picking, or just fishing is called. They're calling it data mining because there is a history of referring to that. It's different from what you guys are doing. Thou shalt be willing to compromise. And he has a wonderful little story here. It's from a paper in 1959. Econometric theory is like an exquisitely balanced French recipe, spelling out precisely how many turns to mix the sauce, how many carats of spice to add, and how many milliseconds to bake the mixture at exactly 474 degrees of temperature. But when the statistical cook turns to raw materials, he finds that hearts of cactus fruit are unavailable, so he substitutes chunks of cantaloupe. Where the recipe calls for vermicelli, he uses shredded wheat. And he substitutes green garment dye for curry, ping pong balls for turtle's eggs, and for Chafougnac vintage 1883, a can of turpentine. The idea here being, the procedures are built with specific expectations that are very, very rarely met in reality. Some of those violations don't matter. For instance, certain statistical procedures are robust to sometimes extreme violations of their assumptions, violations of normality or homogeneity of variance. And it can deviate a long ways and you don't get in trouble. Other ones are going to fall apart very quickly. The problem is you need to know which ones. And you need to know what you can fudge and what you can't. So anyhow, he says, be willing to compromise because you will never meet the exact requirements. Thou shalt not confuse significance with substance. Thou shalt confess in the presence of sensitivity. Have any of you actually performed a sensitivity analysis when you were done with a project? Yeah. Did it change things? Yeah, you see, you do your analysis with certain assumptions. Like, so let's say it costs this much to make the widget, then I do all this other stuff. I say, well, what if the cost goes up, or what if shipping prices change, or what if labor changes, or what if the factory burns down? Oh no, we've got a disaster then. And so sensitivity is a way of changing the assumptions to see how sensitive your conclusions are to that. Hopefully they don't change enormously, but anyhow. There's the reference. I'll put that online for you. That's the end of that. Okay. Back to the 12 steps. Interpret the model. What do the results mean? And specifically, why did they go that way? Now, this is tricky because this is a why question. I'm asking for a causal interpretation. And I know that very often people say, well, I can't give a causal interpretation. I'm going to speak at a correlational level. And I just have to say basically bullshit. You're going to do causality whether you mean to or not. It's going to happen. You have to be prepared for it. You may be able to say, maybe this causes this, maybe that causes that. And then you can start looking at associations between other variables and see what's in there. You have to have some understanding of what's going on in there. This is where I get into database storytelling. It's narrative analysis, not the analysis of narratives, but it's telling a narrative about the analysis that you performed. This is a very big part. And if you're working for a non-technological client, this is going to be a very big part of what they're looking for. Why did that happen? You need to have an explanation. Those of you who are working in predictive analytics say, I use a black box. I do not have to do this. Well, you're not exempt. I have a little parable here. You guys ever seen Breaking Bad? Did you see the first episode of season 4, known as Box Cutter? So here we have the methamphetamine lab. And here in the back, we got Victor, the thug, who says he can run the lab, he can cook the meth, but he doesn't know how. He cannot explain the theory behind it. Then we got Walt up here, who starts rattling off the chemical theory and mentioning, he said, by the way, what do you do when the humidity changes? And as you may recall, Gus the boss decides to go with the people who can explain the theory. You got to know it. Victor meets a very bad end very soon. People who do black box models without knowing what's going on in there, it can be a very bad ending. Because crazy things can and do happen, and you have to be able to diagnose what's going on. Okay, and present the model. So you're not done until you can turn it over to your client. You guys know that a big part of the global data competition actually is presenting your results, because this is not a predictive analytics competition. It's not a matter of lowering your root mean squared error. It's a matter of making a persuasive argument about why your analysis is better than somebody else's. You have to present the model. So, go back to the original goal, see what it is. Hopefully you still got that little sticky on your computer 6 weeks later that says, what were we trying to do? Address the business needs of your client, always exclusively only. This is what you need to do. Give actionable steps. You guys know, for instance, never assume that they will put 2 and 2 together. You're going to say, therefore, you need to make more of these widgets and fewer of these. And if you have market over here to this group, you'll get more sales over here. Very specific stuff. And keep it simple. A general rule of thumb, I've heard is basically, and I realize I have violated this. I have 70 slides. 6 is probably a good number, maybe 3 charts, because that's about all. One of the things I learned about pedagogy and teaching, and this is an argument against long classes, is I say really after about 10 minutes, people stop paying attention, which I can imagine could be here. But, and generally then in a lecture, people learn one thing. Or let me rephrase that. They remember one thing long enough to do something with it. The same is going to be true for your clients. So you want to make it as specific as possible. One of the nice things about the data dive we did down in Utah County is that the Springfield Museum of Art did have a very specific question, and it was this: should we be open on Sundays? And they had data. They said, well, we're open for this many hours on Sundays and we have these special events on here. Is it worth paying the money to keep the place open based on the amount of visits that we get? So it was a yes/no question. Finally, deploy the model. If you got a data product, again, like I said, like a recommendation engine or a friend finder, stick it online, see how it works. If you developed a predictive model on a subset of data, put it on the full data set. Keeping in mind, things don't always scale well. Part of that is because when you get to very large data sets, which happen with either going to your large predictive analytics problem or to your data product, you will get the edge cases that can throw things off. Or, if you're an academic researcher like me, you publish the research. And the last step, 12, is revisit the model. So this is after it's all been done, it's been running for a little while. If your client is your company, if it's your employer, this is really easy to do. If it's not, if it's an external client, you may want to set up some sort of way of following up with them to see 6 months down the road, how are things going? The reason for that is, business models change. How many of you are familiar with the Netflix Prize? It was a huge event from several years ago, not that many years ago, where Netflix was offering $1 million to anybody who could improve their recommendation by 10%. And it got enormous amounts of really fabulous work that was going into it. You know what happened with the Netflix Prize? You know what happened with that algorithm? They never used it. And you know why? Well, that's part of it, but the part of it is that algorithm was developed for the DVD rentals. At the same time, they switched over to streaming. The Netflix DVDs, you have to anticipate days or weeks ahead what you're gonna watch. But streaming, it's right here, right now. And what's really funny is in my field in social psychology, they say people have very different preferences for the immediate and for the long term. Everybody wants to read War and Peace or Sense and Sensibility eventually, but right now they're gonna read something trashy. And I say, I'm going to go watch some Jean-Luc Godard films, but first I'm going to go see the Avengers, And so the preference systems are fundamentally different. The same thing happened. Netflix developed this huge system. It was very elaborate. It was very complicated because it was an ensemble model, but their business changed in the meantime. Another one is context change. And the good example of that one is Google Flu Trends, which I know we've talked about before. Google found during the swine flu that they could use search patterns to estimate the level of swine flu in various places. And they were able to do it very quickly, and they were able to do it with a surprising level of accuracy and get that to the Centers for Disease Control. It was great. Guess what? Doesn't work as well these days. It's in fact, the accuracy of Google Flu Trends has been kind of steadily going downhill. Now, it's not because Google's stupid. Google is smart, but what it is they say, is that the way people use Google has fundamentally changed. And it's made it much harder the same algorithm no longer applies, and it's also harder to just modify it to get back to where it was. Interestingly, I saw other research that said that web searches just on Wikipedia can be used to estimate disease outbreaks just as accurately. So fascinating stuff. So that is step 12 of my presentation, and the idea here is you need to plan. You need, when you get a project, to spend at least a little bit of time running through the steps. I love the awesome thing. I'll give you the references for that. And Hadley Wickham's Tidy Data and Jeff Leake's How to Share Data with Statisticians are great ways to get started. I'll make the slides of this available. I've already recorded and edited the videos, and they'll be up online later tonight. I just wanted to finish with a couple of things. Since we had Moses earlier, I thought it was just fair to finish with Pharaoh. So I'll let it be done and plan appropriately. This, by the way, is my business, datalab.cc, and down there at /blog is where you'll be able to get the links to everything. I will also send the information to Nick and to Pat, who can send it out to you guys as appropriate. Then you can all be super planning geniuses. Thank you. Anything else? We're good. Totally good.
Any questions?
Yes.
Do you find yourself steering more towards like parametric model versus non-parametric, maybe with analysis? Like some things you have to do like a whole series of analysis just to come up with your model.
You know, the fact is my training and my background is in experimental social psychology. We have extremely small data sets and they're extremely clean. And they are designed with a specific analysis approach in mind. And so when you get it, you know, it takes forever to get the data, and 100 cases is a large data set. But once you get it, it's just boom, 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 boom. And you do it that way. Usually, you never do more than a two-factor analysis of variance. You don't even do multiple regression because you specifically, with an experimental design, you've tried to randomize all of those factors. You're left with a very simple thing. That's what I deal with mostly. And that's not what you guys deal with mostly. On the other hand, when dealing with an unknown data set, I know I have to try about a million different things. The risk, of course, oh shoot. I did not specifically address this. Validating your model. And that's because that's going to tap into, whenever you build a model, you need to be able to validate it. And I remember when I first read about that as being an interview question that would sink people coming in for data science interviews. They talk all about how to use this, how to use that. They go, how do you validate your model? Validate what? You see, in my field, the idea is that the assumption, we don't have enough data. We cannot set aside the cases. You know, when it takes you about 7 hours per case, you know, you're going to do, you know, in terms of total time frame, you're not going to do it. But there are other ways to validate the model. And in terms of, it's fine to fish around and try to do the exploratory analyses and try a series of different models, a series of different approaches, but whatever you do, you have to be able to validate it in one way or another. You guys know, of course, the golden rule, if you have a large data set, you set aside a test portion that you just don't touch until you're ready to go, and you only touch it once. And the idea is because if you do it more than once, then you start tailoring towards the peculiarities of that data set, which you're not supposed to do. I know it doesn't really work that way necessarily in real life, but that's the theory. But you should add that. You need to have at least a plan for validating your model in some way. In my field, that's going to consist primarily of showing that there's nothing that could possibly go wrong. That the data are so incredibly homogeneous, that they fit the assumptions so well, and you can do that with strictly experimental research. But that's a different thing. Thanks, folks.
Hey, feel free to lean over if there's extra water.